Momentum is very closely tied to Newton's third law. For every action, there's an equal and opposite reaction. And the definition for momentum is a little bit lengthier than this, but I like to think that momentum is just mass in motion. Momentum is depicted by the lowercase letter p, not to be confused with power, which is the uppercase p, and it's measured in kilogram meters per second. The formula for momentum, lowercase p, equals mass times velocity, and it is really that simple. Um, when we talk about the law of conservation of momentum, it gets to seem a little bit trickier. However, it's really just this formula over and over and over again. Anytime you think of momentum, you also need to think of Newton's third law. So sometimes when we have two objects that are pushing against each other on a frictionless surface, because usually we're talking about momentum, it's frictionless, they're going to exert the same force, equal but opposite, and in that case, they are both going to have the same momentum, equal but opposite. So their net momentum is going to be zero, much like their net force. This gets us into the law of conservation of momentum. Conservation just means nothing is created or destroyed, it's only changed. And this is true for energy, it's true for momentum, it's true for all kinds of different things. When we talk about the law of conservation of momentum, we have to think about collisions, because this is when we're actually changing our momentum. So collisions, there's two different types. And really you can break them into perfectly or imperfectly, but we're going to keep them simple. So we have elastic collisions, and we have inelastic collisions. I lovingly call elastic collisions the hit and bounce, because that's what they do. And then the inelastic are the hit and stick. The formulas for the conservation of momentums, no matter which type of collision it is, are pretty much the same, but we can write them in different ways so that we can attribute it to that type of collision. So for elastic, we have M1v1 plus M2v2 equals M1v1 final plus M2v2 final. What this means is that I have one object that's moving at a certain velocity, and it's going to hit another object that's moving at a separate velocity. Once those two collide, their velocities are going to change, and sometimes even their directions, because velocity is a vector. But their momentums will not be the same as when they began their voyage. Inelastic is the same formula. However, after the collision, they are both moving at the same velocity. So for this one, M1v1 plus M2v2 gives me M1v final plus M2v final. Both of those velocities are the same, so I can even simplify this formula by saying M1v1 plus M2v2 equals M1 plus M2 multiplied by V final. Momentum is one of those that is very helpful when you draw pictures of the collisions, because that way you can actually determine whether they are moving separately or which one's going faster, so forth and so on. The last part of momentum that we need to talk about is impulse momentum. Impulse is characterized by the capital letter J, and it's really the change in momentum. So changes in momentum usually we attribute to things like car crashes or running into things, slowing and stopping very quickly or slowly depending on what it is. So when we're talking about impulse momentum, I want you to think of a change in momentum, and that's exactly what it is. It's final momentum minus initial momentum, because that is what the delta means. And that's equal to a force that's applied over a period of time or during a period of time. So impulse, change in momentum, force, applied during a period of time. So here's where we get into seatbelts and why we have seatbelts and why they're so important. Seatbelts apply an impulse to you so you don't go flying through a windshield. No matter what, your impulse change is going to be the same. What does change, however, is the period of time that you are exerting a force on an object, or your seatbelt is exerting a force on you. If you're coming to a stoplight, and you slam on your brakes, when you slam on the brakes, you create tire tracks, and you end up stopped. You also may end up with a seatbelt bruise, just because your seatbelt kept you from flying through the car. When you apply a brake, your car is what the brake is being applied to, not you. When you're both traveling 60 miles per hour, you're going 60 miles per hour, the car is going 60 miles per hour. You slam on that brake, that car is decreasing in velocity. However, you are not. You are continuing at 60 miles per hour. Slamming on the brake versus gradually applying the brake is going to decrease the amount of force that is going to be applied to you. So as the time increases, force decreases. Your change in momentum stays the same. So this is where we get the impulse aspect. Higher force, less time. A lot of people do the egg drop test. And in that egg drop test, you have an egg and you're putting it in a cage and you're dropping it from some stairs and you're hoping that it doesn't break on the ground. In order to help that egg from not breaking, you need to make sure that there's a lot of cushion underneath, because what this cushion is going to do is it's going to slow the rate that the egg is falling before it hits the ground. A lot of times, if you drop something on grass or a blanket or anything that'll slow it down, it's still going to have that same change of momentum, but it's not going to have as much force applied to it because that time period is greater, causing less impact.